Welcome everyone to our latest dedicated computing webcast, the impact of AI within the healthcare and medical device market. I'm your host, Gareth Harwood, Director of Marketing at Dedicated Computing. We're joined today by two subject matter experts, Carl Flygare from PNY Technologies. Carl is the NVIDIA Quadro Product Marketing Manager with over 25 years in the industry. Thank you, Carl, for being here. And joining us from Dedicated Computing, also with over 20 years in the industry, is Jeff Krueger, Director of Systems Engineering. Thank you for being here. Jeff, we will start with you. So Dedicated is helping many of the world's largest medical device manufacturers with system design from an advanced computational platform perspective. What are you seeing out there among our customer base for how they're preparing for AI, machine learning, and other emerging technologies?
Yes, so as AI, data analytics, all of this results in larger amounts of data to process, requiring even more computational capability within a compute node. In order to do this in the past, many of these folks relied on the clock speed of the CPU to get faster to improve their application speeds, but that's no longer viable. So in order to compete and to incorporate some of this large processing, there is an evolution happening with which I'm calling heterogeneous parallel computing. That architecture allows for multiple different types of computational blocks to be within a computer. That is a CPU, it could be GPUs or multiple GPUs, FPGAs, or algorithm-specific ASICs. These computational blocks help move away from some of the proprietary devices that we've used in the past to acquire signals that result in us having data to turn into imaging and processing. It also gives some of the flexibility in updating and processing that application into the future. So this hardware and software parallel architectures are the thing that are going to create some of the challenges for the OEMs. When we start integrating a CPU, two GPUs, and an FPGA into a single box to do many levels of parallel workload on each one, the shift really focuses back onto the software developer to make it all work, along with understanding some of those compute blocks and how they align to make them very purpose specific in their approach. Where some of the problems come in for the OEMs is they're not always familiar with what the CPUs can do, the GPUs, the FPGAs, the ASICs, how it all lines up. So because they're focused on their product and their solution, their software developers are focused on developing their solution and not necessarily worrying about how everything aligns. So that's really where we're helping move that landscape forward.
Great. Good stuff. Thank you. Carl, thank you again for being here. There's a lot of great press out there from NVIDIA where they're headed with medical imaging and AI. Help us break it down to that hardware level and what it means for medical device manufacturers.
Well, thank you very much for the introduction. And as mentioned, we'll be talking about GPU-enhanced medical imaging systems. There is obviously the visualization, the imaging component, and a very powerful AI component. Let's go ahead and get started. I've known a gentleman named John Petty for more than a few decades. He is in charge of John Petty Research, which is one of the most widely known industry analysts and pundits that tracks the developments in GPU technology. And when NVIDIA announced RTX technology and products like Quadro RTX at SIGGRAPH in Vancouver almost 2 years ago, he basically said this is a significant moment in the history of computer graphics. NVIDIA is delivering real-time ray tracing 5 years before we had thought possible. Well, why would I open up a medical imaging webinar AI webinar with ray tracing. When most people think of ray tracing, they think of games. But ray tracing is really modeling the behavior of light and real materials in physical space. And if you think about it for a moment, medical imaging systems use the electromagnetic spectrum. They can use X-rays and CT scanners. PET uses gamma rays. So the fact of the matter is these ray tracing technologies and the engines that accelerate them are just as applicable to medical imaging as they would be, say, to an architect trying to design a structure, an engineer trying to design a product. Quadro RTX and Pascal GPUs, because we have two concurrent product architectures, have been widely accepted and adopted across medical imaging providers. A couple of folks actually that I work with, one's in the Bay Area, Siemens, they're just up the road, about 20 minutes, have embraced Quadro. GE Healthcare is another. My understanding is both these firms also work with dedicated computing. And in addition, our product portfolio includes vendors like ISO, NEC, AGFA, and Philips. So all of the major vendors that are trying to deliver leading edge solutions have realized the value of GPUs in them. With Quadro RTX, we probably took the single largest leap in 12 years or so since 2006 when the CUDA GPU came to market. First, we completely re-architected the multiprocessor design and made it much more efficient and allowed for concurrent floating point and integer execution. We added something called RT cores, which are the ray tracing cores, which can handle the path of rays of light or other frequencies in the electromagnetic spectrum at up to 10 billion rays per second. We've also added Tensor cores, which are custom purpose-built to accelerate artificial intelligence, and we push things forward dramatically in the display front, up to 8K, native high dynamic range, a technology called VirtualLink that I'll talk about in a moment, and a bridging technology known as NVLink that, if you need even more power than one Quadro can offer, gives you the ability to merge two boards together into a single logical entity. So when I talk about Quadro RTX at a high level, think of it as a synergistic fusion of ray tracing, deep learning, and advanced shading for medical imaging applications. The RT cores do the real-time ray tracing up to 25 times faster than the Pascal, the prior generation CPUs. You can render photorealistic effects at 30 times the speed of CPUs. Tensor cores power AI-augmented applications, things like resolution scaling or AI denoising, training deep neural networks to go in and potentially diagnose, different medical conditions and act as an assistant to the clinician, be they a doctor or some other practitioner, and the advanced shaders that let us deliver the highest quality images possible. We'll dive into each of these in a little more detail momentarily, starting with the advanced shaders. The first is something called mesh shading. Parallelism was mentioned early on. Anything that can allow the CPU and GPU to operate more harmoniously with less interrupts to each other increases overall parallelism within the system and the application. Mesh shading enables that. Another that's very important is something called variable rate shading. In medical imaging, it may be essential, but a key component of a given image is always presented at the absolute highest quality fidelity, particularly if you're using something like virtual reality. Variable rate shading will let a developer go in and control which components of an image will always receive maximum GPU cycles and be presented with the highest possible degree of visual integrity. Texture space shading is another way to improve efficiency by reusing shading results. And multi-view rendering, particularly in a VR context, is extremely important because in a single pass of the GPU, it can generate up to 4 independent views. So in the context of robotically assisted surgery or augmented reality or virtual reality assisted medical techniques, it can make a huge difference. VR has been very much bumped up. VR has been experiencing widespread adoption across professional markets. One of them is medical imaging and healthcare. Specifically, things like variable rate shading let the GPU optimize itself to whatever head-mounted display a given medical imaging provider cares to use. You can do things like matched lens optics, which will differ in the system. You can provide something called foveated rendering, which places the most detail where the human eye is most sensitive, a region known as the fovea. The single pass stereo, I kind of alluded to. You could generate up to 4 independent views in a single pass of data through the GPU for the head-mounted display. A wide field of view, because you want a field of view that approximates that the eye-brain system delivers in real space. Well, now you can do that. VirtualLink is an open industry standard that makes it much easier, much simpler to integrate a head-mounted display into a system. Instead of needing cables for power, for data back and forth between the HMD and video, a single cable handles all three. And when it comes to performance, the rasterization, the shading optimizations, the ray tracing acceleration, not only improve graphics performance, but can also be used for audio processing. And in extreme edge cases, you can even assign one graphics card to the left eye, a second to the right eye, something we call dual input VR SLI. I've talked about most of these, but a couple of other points. The field of view is critically important. Visual quality is critically important. These are healthcare procedures. These are practitioners performing the most mission critical of all tasks, healing people. No card, no architecture can do that better than Quadro RTX. VirtualLink, I touched on before. You see here a VirtualLink port. It's a USB Type-C connector, which is more or less ubiquitous. It's in the back of all the Quadro RTX cards, and will let you drive the latest generation of HMDs. A very important point to make about Quadro RTX, particularly pertaining to medical imaging in general, but also VR in particular, is more GPU memory is a very good thing. And cards like the RTX 6000 or RTX 8000 with 24 gigabytes or 48 gigabytes of GPU memory offer much more than the gaming cards, the GeForce boards like the 2080 Ti or 2080 Ti Super or the RTX 2080. This bar chart calls it out. This gives you the ability to work with even the most complex VR medical environments with complete fidelity, without having to worry about slowdowns that may be encountered by moving things from GPU memory to CPU memory, which gives you more control over navigating where you may have a panoramic experience. You can use more complex textures. You can use very realistic light fields. So you can generate much more accurate results than you could with a more limited amount of GPU memory. I alluded earlier to something called NVLink. NVLink pools GPU memory and scales performance of Quadro RTX boards. I like to think of it as kind of like a Vulkan mind meld. It takes two minds, two GPUs, and merges them into one. So for example, if you had dual RTX 8000s, you would end up with 96 gigabytes of available GPU memory. You'd have twice the CUDA cores, twice the RT cores. The same thing applies to the RTX 6000. You can go from 24 gigs times 2 to 48 gigabytes, and similar, performance upscaling because of the additional cores that are brought into the equation. NVLink communicates much more quickly than PCI Gen 3, 100 gigabytes per second in the case of the RTX 8000 or 6000, up to 50 gigabytes per second in the case of the RTX 5000. So this gives you the chance to build headroom into your system. If a single Quadro board can't accommodate it, you have a way to realize even the most demanding needs by adding a second card. There are some real advantages to this because, again, if you're doing, say, taking the results of a PET scan and generating an image, you may be rendering extremely detailed imagery. And if you're working in a VR environment, VR can actually take significantly more bandwidth than 4K video. In fact, it can approach 8K video. If you look at across different industries, including healthcare, the average amount of GPU memory used to do really accurate state-of-the-art renders, you're looking at about 34 gigabytes on average. Now, obviously, I'm talking very high-end here. If you're an ultrasound device, it won't be near this. At the extreme high-end, you can be looking at up to 75 gigabytes. Quadro RTX is the only solution available today with NVLink technology that will let you hit those points with 48 gigabytes and 96 gigabytes of GPU memory availability. The Tensor cores, here's where we're going to shift gears a little bit, really are designed to accelerate deep learning, machine learning, and machine vision. They do this through a fuse, multiply, and accumulate operation. It's matrix arithmetic, which is foundational to the deep neural networks of various types that are used in domain-specific artificial intelligence in medical and healthcare systems today. NVIDIA has gone so far as to develop something called NVIDIA Clara Medical Imaging. This is an SDK for medical imaging providers that let you take advantage of tens of millions of dollars of NVIDIA NRE, non-recoverable engineering expense. They've done all the low-level work of integrating AI, and you as a developer can come in at a much higher level. The NVIDIA Clara is foundationally based on something called CUDA-X AI, NVIDIA CUDA-X AI, which has data analytics, graphics, machine learning, deep learning training, and deep learning inference modules. It's highly scalable. You can do the development work on a workstation, do test deployments or clinical trials perhaps on some servers, and do a wide-scale deployment in the cloud, all without having to worry about touching your code. And it works with all the common frameworks available today, folks like Chainer, PyTorch, TensorFlow, compatible with all the leading cloud services, be it Amazon Web, Google, Azure from Microsoft. And when it comes to the deployment options, you pretty much have your choice of all the leading ones available today. So NVIDIA has made it far easier for you using Quadro RTX from a hardware and a software perspective to bring artificial intelligence into medical imaging and healthcare applications. Now, I don't have access to proprietary medical information. That's why we have things like HIPAA laws. So mortgage data is something I did do some work with. And I actually found that doing the data prep, the ETL, it was 30 times faster than the CPU. If I was doing training using the very widely and well-known XGBoost development environment, 8 times faster than CPU. And the total end-to-end performance of the entire system, from doing the initial data prep to training to getting acceptable levels of inferencing performance, was tenfold better than the CPU can deliver. So in terms of time to market implications, in terms of the training as new data becomes available, and GPU systems simply outclass anything that a CPU can offer. Rapids is part of the CUDA-X AI and the Clara environment. It's a data structure with very low latency, so it's widely used by data science professionals, including in medicine and healthcare. Here you see the kind of performance you'll get with 2 Quadro RTX 8000s versus a single RTX 8000 versus a CPU. The results are not subtle. You do get what you pay for. Again, CPU-based systems simply not competitive with what GPUs offer today. Now, Quadro is a very broad product family. So I want to make a key point here. If all you need to do is drive some, 10 or 12-bit grayscale displays or color displays for medical imaging purposes, even our entry-level boards support DICOM and DCC. If you go up a step, the P2000 in particular is very popular in the ultrasound space for doing not just the image processing, but other aspects of ultrasound imagery such as beamforming. If you step up another notch, you begin to see the first RTX product, the RTX 4000. So here we're now in a high dynamic range color space, the advanced shading, the Tensor cores, the RT cores. If we go beyond that with the RTX 5000, we basically double the amount of GPU memory, come close to doubling the amount of CUDA cores, significant improvements to Tensor core count, RT core count, and we bring NVLink scalability to the party. Beyond that, we start getting in the heady space of the RTX 6000 and the RTX 8000. These are really kind of the ultimate products that NVIDIA is capable of building today. Unprecedented amounts of GPU memory, unprecedented AI performance, unprecedented rendering performance. And that's rendering whether you're using ray tracing or traditional rasterization rendering pipelines. We're going to take a quick deep dive into some of the products, starting with the 8000. Again, this is the 800-pound gorilla of Quadro. Tremendous CUDA core count, 576 of the Tensor cores for AI acceleration, 72 of the RT cores for real-time ray tracing, which again can handle X-rays, gamma rays, so widely applicable to medical imaging devices. The 48 gigabytes of GDDR6 is the next generation memory technology. It does support optional error correction. That's something you can turn on or off. I'm going to jump down to a deep learning T-flops. You see 130.5 Tensor teraflops from a single card. So for AI enhancement, a tremendous asset. NVLink support lets you gang up to these cards with near linear performance scaling. And the total power draw, if you're not using the VirtualLink port, is still only about 260 watts, so not significantly different from the prior generation GB100 or GP100 products. A step down, the Quadro RTX 6000 really provides exactly the same compute and graphics and AI performance as the RTX 8000. It just takes the amount of GPU memory down to 24 gigabytes from 48 gigabytes. So other than that, these two cards are identical. You can save money if you don't need the additional memory the RTX 8000 offers. 6000 is a more economical choice to consider integrating into your system. If we look at graphics performance, it's interesting. This is spec view perf. I'm showing prior generation Pascal and Gen -2, which is the Maxwell architecture. The area where the RTX 6000 or RTX 8000 actually delivered the greatest overall spec view perf results were the medical imaging, medical diagnostics, medical imaging test suite. So tremendous performance relative to even the Pascal architecture cards. If we look at the competition, in this case, the AMD WX9100, I've set the AMD results to 1. You can see the results for medical. We're outpacing them almost by a factor of 3, really. It's a little unfair to compare these cards because the fact of the matter is AMD lacks RT cores. They lack Tensor cores. So they can't do the very sophisticated rendering that ray tracing requires with hardware acceleration. And they simply can't accelerate the kinds of AI that are becoming ever more essential to medical imaging systems. The RTX 5000 do take down the CUDA core count. We do take down the Tensor core count, the RT core count, as well as the GPU memory to 16 gigabytes. But we still support ECC. And very importantly, we still support the NVLink. In spite of these reductions in core counts, you can still generate up to 8 billion rays per second using the RT cores, and you still have access to almost 90 teraflops of deep learning performance for AI augmentation of your applications. And if you look at Quadro RTX 5000 graphics performance, again, another area where it dramatically improved over the Gen -2 M5000 are the medical results. Pascal is still fairly close, but the fact of the matter is medical systems have a fairly long life, so a lot of folks may still be using the Gen -2 product. If so, it is very much in your interest to consider Quadro RTX 5000 for your next project, or perhaps as an upgrade to a series of existing products. Again, when it comes to competitive analysis, I'm comparing the RTX 5000 here to the AMD WX8200 and WX9100. As I mentioned before, the AMD products don't have the RT cores for the ray tracing. They don't have the Tensor cores for the AI, but the simple fact of the matter is we significantly outperform them, including in medical, where in fact, again, that was the standout at 2.35 times what AMD's best could offer. The final card I'd like to mention is the Quadro RTX 4000. This is the world's most powerful single slot professional graphics card. So if you're looking at a system context where a dual slot with board wouldn't be acceptable, this is a great choice. Still a good CUDA core count, 8 gigabytes of GDDR6 with optional ECC, nearly 60 Tensor teraflops of performance, and you still have the VirtualLink support across all of these cards for doing, VR in the medical context. So Quadro 8000, 6000, 5000, 4000, all of the RTX boards deserve a very close look. Again, great performance with the RTX 4000, and again, medical, it literally topped the chart at little over 3 times the performance of the Gem-2 M4000, and still delivered significantly better performance than the Pascal architecture P4000. And again, in medical, 2.84 times faster than the corresponding AMD product. So again, Quadro is pretty much establishing a performance benchmark for medical and healthcare applications. So why Quadro RTX when you can go out and buy a GeForce card? Well, the fact of the matter is Quadro boards are designed for workstations, for environments like medical imaging, healthcare, diagnostic milieus, where GeForce is designed for PCs and gaming. Quadro comes with a whole series of brand promises from NVIDIA and PNY, highly tuned drivers, large amounts of GPU memory, scalable performance with a technology like NVLink. Just as important as the hardware, mission-critical drivers, long-life stable drivers, so that you don't constantly need to worry about revving a new driver into a product, given the regulatory environment you operate under. If you want to use off-the-shelf software to complement what you're developing, over 100 professional applications are pre-certified for use on Quadro. In terms of IT management, very important in a healthcare environment, the ability to diagnose, remotely troubleshoot systems. Quadro offers all those capabilities. GeForce simply does not have them, which makes Quadro RTX the right choice for professionals. It will deliver better professional application performance, including medical, gives you access to advanced professional features, performance scaling, mission-critical drivers, certified by all the major medical system providers today, and has the IT management tools that will make it easy to fit a solution that contains Quadro as part of the solutions component into a managed IT environment. That said, I would like to turn it back to our partners at Dedicated and let them close out the presentation.
Great, thank you very much, Carl. Excellent, excellent stuff. Jeff, thank you for joining us. For any audience members who have questions or want more information, you can see the contact information for each of us on the screen. Feel free to reach out to us at any time. If you're on social media, please don't forget to follow Dedicated Computing on LinkedIn and on Twitter @Dedicated. That concludes this version of a DC webcast. Thank you very much for joining.